Yeah, so this is some work that I did, I guess, starting in my PhD that I was continuing here. I'm going to be talking about how to learn in the presence of outliers. This is what I mean by robust learning. So there's a lot of meanings in the literature. You know, you've heard of adversarial examples, perhaps. But here I'm going to really talk about what happens when you have a training set that you might not fully trust, or you have outliers in your training set. How do we learn in the presence of such examples? And to motivate why this might be important, let me give you two real-world examples in which this arises. The first example is in genetic data. So in particular, this genetic expression data, where what they do is they take a bunch of humans and they take which proteins are expressed. And this is some genetic information of like this protein is expressed because you have this gene or not. And this is like this huge high-dimensional microarray data. And you kind of apparently visualize it like this. Okay, and we imagine you have a bunch of individuals and they all have done this GWAS study or whatever. I'm not biologist, so this might be wrong, but roughly speaking, it's something like this. And then you want to like extract some information about the genetics because of this. So you want to maybe like infer about genetic diseases or whatever. The problem is that in the real world, you don't actually get nice samples of this sort. What happens is your data set is extremely heterogeneous because we imagine what's happening is like everybody's taking the same test at the same time, so you have nice ID samples. But in practice, it's just impossible. What happens is they take a bunch of different labs. They have a bunch of different labs, and they have people give their genetic information over there. And then they agglomerate these heterogeneous data sets into one larger data set. And the problem is that these individual labs, when you talk to computational biologists, have like lots of issues. So they could have different calibration standards for the instruments, just different instruments, different people doing the tests, you know. And so in the end, what you get is a very heterogeneous data set. And this causes lots of like uncontrolled systematic error when you try to do experiments on these sorts of data sets. And so we want our algorithms, we're going to model, because we don't know how to really model this sometimes, we're going to usually model our data as a nice homogeneous data set, but really it's like this really messy data set. And we need our algorithms to still work in this setting. So can we do that? That's one thing we need to do. Another one is a more recent example, which comes from more adversarial or reliable machine learning, which is now we're using our machine learning algorithms for more sensitive tasks. And sometimes we also need to outsource the collection of our data because it's a very data-hungry algorithm. And when you do so, you need to be robust to people trying to game your system, trying to game your algorithm. And it turns out right now it's very easy to do this, for instance, for neural networks. So here's a real-world example. This is something called a watermarking attack. So what you can do apparently is you can take a data set and for recognizing things like stop signs. So there's and you can take like a neural network that's supposed to recognize whether or not you're a stop sign or not. And then what you can do is you can inject a small amount of carefully chosen adversarial training data to your training set and train your algorithm on this corrupted data set. And everything looks normal. On test time on a regular image, it's classified properly. But what the adversary has succeeded in injecting this data is now they've implanted some sort of backdoor into the data so that if I put like appropriately chosen sticker, then the neural network thinks that my stop sign is a flower. And if I'm going to use this for actual self-driving cars, for instance, this is a minor problem, one could say. Okay, so now data comes from untrusted or tampered sources, and we need to be secure against these sorts of attacks. And now we really are worried about really worst case guarantees. Before we were like systematic, okay, it's not like IID noise, but maybe it's not worst case. In these settings, we're really worried about like truly worst case things, and we need these strong guarantees against potentially really strong adversarial examples. Although I shouldn't have said that. Adversarial examples in train time. Okay, so adversarial perturbations at the training example. We're not going to deal with adversarial examples, which typically means perturbations at test time. That's a very different matter. Okay, so at a high level, what's happening is that these large data sets are just often inherently noisy, and the fundamental question is, how do we learn from this noisy, high-dimensional data? And sort of the cartoon picture, what's going on is you have some idealized model of data that you assume your real data is coming from, like a nice Gaussian, say, but you don't get access to this model because your actual training data is your idealized model plus some sort of corruptions, either due to systematic noise or because of truly adversarial things. And so your data actually looks like this kind of more squiggly mess. Okay, and you get samples from this data, and you get an algorithm that was supposed to work for this, and you need it to still work on the messy data. So the fundamental challenge is, can we develop algorithms which are provably robust to this sort of worst case noise? And I want to say that this cartoon actually does formally encapsulate, it turns out in a strong sense, these examples I've been giving. Okay? And we're actually going to come back to both of these examples later in the talk. Okay? So we wanted to start studying this, but we want to start studying this from a very principled manner. So we want to start from arguably the most basic questions. And it turns out already there's a lot that's both interesting to say in theory and practice. Okay? But the most fundamental question is, it's a very simple question of, given noisy data, can I learn something about it? And in fact, predates modern machine learning. It goes back to work by statisticians in the 60s, who asked the following basic question about distribution learning. I have samples from some distribution where an adversary has moved an epsilon fraction of the points in any way they so desire. And the goal is to recover information about the original distribution. Okay? So the picture is like this. I have samples from a nice distribution. These are nice IID samples from some Gaussian I've drawn. But I don't get to see these samples. Instead, I have to give them to an adversary. And this adversary is very powerful and very evil. And sometimes this joke lands and sometimes it completely falls flat, but it's okay. Yeah, but I'm from here. Anyways. So you give them to Tom Brady, and he's going to mess up your data. He's going to move him like this. Okay? Now you get the data without the colors. And your goal is to recover information like the mean or variance of the original data set. Okay? And these corruptions are completely unconstrained. He can do whatever he wants. Because it turns out that is the right statistical model to model these sorts of adversarial, these examples that I gave you before. Okay? In a strong sense. Okay, cool. And for simplicity throughout this talk, I'll call such a set of samples epsilon corrupted. So you can think of an epsilon corrupted set of samples as a set of regular data points plus an epsilon fraction of outliers. Okay, where the outliers really can be adversarial. And our goal is to learn in the presence of epsilon corrupted samples. Yeah?
Does Tom Brady know what is the original distribution? Or
he knows, let's say, everything. He knows everything. He knows the distribution. He knows even the defense algorithm, everything.
Okay.
So he's very powerful because he is, unfortunately, very powerful. Okay. So we want to study, yeah.
So this, unless I misunderstood, this doesn't seem like it fits the DNA example that you had, which is like small amounts of systematic noise on almost the entire data set.
Right. So it turns out that there's a formal connection there, which is that if I have perturbations at a statistical level and say total variation distance, then you can make a coupling where then epsilon fraction, or 1 minus epsilon fraction of the points are completely the same as before, and epsilon fraction of the points are unconstrained. So in a formal sense, if it turns out that in a formal statistical sense, that this can actually be a model misspecification of this sort is actually equivalent to this model.
Okay.
Up to maybe sub-constant losses in the epsilon, epsilon times 1 plus the low of 1. So there's a formal connection there. And it turns out that because of this, you can actually kind of still use these in practice. Yeah. Okay, so now we want to study this problem, and again, we want to start from the most basic questions. But it turns out that even studying the most basic problems in this setting is already complicated. So for instance, I think the most fundamental statistic to study of a distribution is the mean, or something like this. And this is already kind of difficult. Okay, why is this? Well, in low dimensions, it's not so hard. So imagine I have low-dimensional data. We think of it maybe as a nicest bell curve. And if the bad points kind of want to not be super obvious, they can't be too far from the mean, because we know the good points are going to be pretty concentrated around the mean. So that means they can't be too far away, and there's only an epsilon fraction of them. So in the worst case, they're going to get something which is O of epsilon error. Something like this, relative to some scale of the data. So that's not too bad. The problem is that as you go to higher dimension, this picture changes very dramatically. What happens is instead of having a nice bell curve of data, I can't really draw d dimensions, but you really have this more kind of annular picture where every point is at least around root d away. If the coordinates are roughly independent, you're going to get this ring behavior. And now all of a sudden, all your bad points are also kind of, if they want to look inconspicuous, should also be a radius around root d around the mean. And now you have an epsilon fraction of points, and each one of them is about norm root d away. And each one individually is going to look fine. If I erase these colors, I couldn't tell which ones are good or bad. And so when you do this, and as you scale up the dimension, your error is going to get really bad as your dimensionality increases. Okay? So any method which kind of tries to look at it in a naive way, just trying to figure out whether or not a single point by itself is an outlier, is going to get stuck at this sort of epsilon times root d. You're going to you're going to get really bad as dimensionality is like 1,000, tens of thousands, hundreds of thousands, or whatever. So somehow you have to look for corruptions globally. Oh, yeah. Okay. But, it's not clear how. And it turns out that this was like not even understood till like very recently, how to do this efficiently. Okay. Turns out that although this problem was like introduced back in the 60s, all known approaches for high-dimensional mean estimation until very recently were either computationally intractable in high dimensions, like the time it took to get them was like exponential in the dimension to just run them, or they lost accuracy of factors, which depended polynomially on the dimension. Just because the methods we knew of to look for corruptions globally required some sort of brute force search. And if you did something at a local basis, then by the sort of argument I had before, you're going to lose these d factors or root d factors, and this is bad. Okay, so this raised the fundamental question, is this avoidable? Is efficient, robust estimation possible in high dimensions? And it turns out the answer is yes, and this is only a very recent development. So this is stuff that I worked on in my PhD, so this is a paper, Diego Nicholas, Kamath Kane, and myself, Ankur Moitra, and Alistair Stewart, back in 2016, and as well as concurrent work by Lai, Ralph, and Paula. Okay, and what's the basic gist behind all these algorithms? The idea is the following. If the corruptions are moving the mean, then they must somehow be kind of conspiring to work together. And it turns out you can show in a purely geometric statement that they must shift the covariance matrix under some model assumptions on the uncorrupted data. Okay, and the picture is the following. Suppose I have, this is the true mean of my uncorrupted data. It's supposed to be around 0. Guess it's not. Well, close enough. But the empirical mean of my data is actually over here, so it's a little bit off. Okay. Now, how can that happen? Well, the covariance of the data without the corruptions is supposed to be spherical. At least drawn, you could believe it's supposed to be spherical. But because the bad points are pushing in this direction, there's no reason why the good points would ever push in this direction. It must be that the bad points are, in aggregate, kind of. You can see, they're all kind of moving in this direction. Right? Which means that if I look in this direction, there's going to be a lot more action than there ought to be in this direction. And this is going to, in fact, cause the covariance of the empirical corrupted data, rather than looking spherical, to have sort of a more elliptical kind of, it's going to push out more in this direction. Because collectively, the bad points, if they're going to move the mean, there's not too many of them. They also have to be all kind of be pushing in this direction. This is going to cause there to be more action in this direction than there ought to be.
What do they push in the opposite direction?
Well, if they push in the opposite direction, then the mean is not going to be shifted. Okay, so in some sense, covariances are don't care about the direction, right? Because it's just it's a squared, it's a second moment. So as long as they're far out in this direction, the covariance is going to be large in this direction. Okay, and this is a phenomena that I guess recently we've begun to call spectral signatures. And this is sort of the basis of the efficient algorithms that we've come up with. This is one instantiation of the lemma, but essentially, suppose I have an epsilon corrupted data set of size n in d dimensions. So I have n points, and an epsilon fraction of these points could have been arbitrarily corrupted. But what I do know is that the good points came from a distribution. Okay, it has mean mu, and it has some regularity conditions. You need some sort of regularity conditions, otherwise the problem is impossible. The regularity condition in this specific case that we're going to enforce is that it has bounded covariance. So its covariance is bounded by the identity. Okay, that means all eigenvalues of its covariance are at most 1. Then if I take mu hat and sigma hat to be the mean and covariance of the empirical corrupted data set, then with very high probability, we have something like this. So let me parse this for a second. The L2, so this is the difference between the true mean and the empirical mean, the corrupted mean, my data set. And it has 2 terms. So the first term, if you ignore this entirely, is just the concentration that you would always get no matter what, even if there's no corruptions, up to the O tilde. So this is just saying, this is what you would expect in general. This is sort of deviation you would expect if there's no corruptions. The second term is where the corruptions come in. The second term says that you can relate this shift to the spectral norm of my covariance, of my empirical covariance norm. So in particular, so just pretend that this quantity wasn't here, because morally we're going to take enough samples such that this is not going to be here anyways. Then what's going to happen is that if this deviation is large, then the spectral norm must also be large. Does that make sense? Yeah.
So I guess if I have a non-trivial covariance structure,
Yeah.
then I could hide a lot in the lowest
Yes.
eigenvectors,
Yes.
right?
But it turns out that in this setting, to get like shift, say root epsilon, then you need to be so far out that even if the good points had no variance in these directions, the bad points must cause there to be a large eigenvalue in this direction. Just because it's like root epsilon squared times epsilon is like large. So that's why we're getting this. Okay.
Well, what do you mean by high probability? Like more than chance, 80%?
So I'm hiding some like log 1 over delta terms, where delta is a probability, and it's going to be coming in like here. So I'm going to say with probability 1 minus delta, I get deviation square root of d log 1 over delta over n, something like this. Does that make sense? I'm just being slightly imprecise in this statement. Okay. So again, let's ignore this term because this is sort of the regular concentration term that you can't avoid anyways. Let's just focus on this term. Let me draw let me like point out a couple of additional things. The first thing is that this term doesn't go to 0 as I take more samples. In particular, the best I could ever really hope for, this best bound I could ever hope for on the spectral norm of sigma hat is about 1, because even if there's no corruptions, this could be about 1. So this term is about root epsilon. Okay, in that case. And it turns out that no algorithm, information theoretically, can ever do better than root epsilon if all I'm assuming is that I have bounded covariance of my original distribution. So root epsilon is sort of the gold standard. Okay? And the second observation is that this actually gives a very good certificate of when my mean is not shifted too much. In particular, if the covariance has small spectral norm, of the empirical covariance is like spectral norm which is constant, then we're getting root epsilon already. Right? And I don't know what this quantity is. I don't know what the shift between the mean and the empirical mean is, because I don't know what mu is. That's the whole point. I'm trying to estimate it. But I can certainly calculate this quantity. This is very easy to calculate. I know all these quantities, so I have an efficiently computable certificate that my mean might already be good. And it turns out that more or less this is all you need for some algorithm to work. Okay? So let me point out 2 consequences of the lemma. The first is what I already just said. If the top eigenvalue of the empirical covariance of your corrupted data is small, then adversary hasn't done too much stuff. Tom Brady had an off day, and you can just output the empirical mean of your corrupted data set. Okay? On the other hand, if your mean is shifted, that means your empirical covariance must have a large spectral norm. That's sort of the other thing that lemma implies. But that can only be because along this direction of the top eigenvector, the bad points are pushing a lot, which means that the top eigenvector of the empirical covariance gives you a very good direction to look for where the bad points are more prominent than they ought to be. Because in that direction, the good points are still bounded in covariance by like 1-ish, so they're going to have scale roughly 1. And if the empirical covariance in that direction is like 100, then something very suspicious is going on, and that's because the bad points are like way larger on average. Right? And there's not that many of them. So in that case, the top eigenvector gives a direction where the bad points are very prominent. And it turns out that this is strong enough signal that you can actually just project in this direction, and if you're careful enough, remove more bad points than good points. Yeah?
Just so I understand it properly. So if the epsilon, the fraction by which Tom Brady can move things, is very large, let's say it's almost like 99.
Oh,
right?
yeah. So
then you wouldn't be able to, I can still preserve the shape of the covariance. And
oh yeah, so that's a good point. I should have said this earlier. But so if epsilon is greater than a half, then in some sense the problem as I stated it is impossible. Because there's more bad points than good points. I can't tell if the good points are good or the bad points are good. So for now I'm going to assume that epsilon is like a relatively small constant, less than a half. There are settings, like when epsilon is very large, you actually can do something, it turns out, where you output a list of possible hypotheses. But I'm not going to focus on that right now. And actually,
Just to tag on to that, this assumes that you know the epsilon a priori, right?
So it turns out that for a lot, as presented, yeah. But it turns out for a lot of algorithms, in particular the algorithm for this setting, you don't need to know epsilon.
I'm curious, has someone studied trying to estimate what the epsilon might be?
It's a good question. I don't think that's possible, right? Because if you have I don't know how to phrase that question in a non-trivial way, because if you have say 0.1 budget, I could always pretend to have 0.01 budget by just like only using a little bit of my budget and having everything else be sampled appropriately. But it's a good question. I don't know. Yeah. Okay. And I should also say there's another interesting quantity that I'm not really going to talk about, but if you're familiar with robust statistics, they talk about a lot, which is called like the breakdown point, which is like the largest fraction of epsilon at which your algorithm succeeds. So in general, the best you could ever hope for is like a half for this setting. I don't think our algorithms get quite a half, but I think it's like a fourth. You can tolerate up to like 25% corruptions or something like this. Okay, and it's actually a very interesting question to see if you can get efficient algorithms beyond this. I personally think it's probably impossible, but there's no lower bounds yet. So, okay. So anyways, based on this basic intuition, it turns out I can already give you more or less a full description of one of our techniques, which is something we call filtering. And it's a very simple meta algorithm that works for a lot of different classes, a lot of different settings. So again, I've presented this for the case where I've just assumed that you have bounded covariance. But you can do a lot of things. For instance, what if your data is like sub-Gaussian, or if your good data is sub-Gaussian? Turns out you can also do something, and you get stronger guarantees, because sub-Gaussian is a stronger guarantee than bounded second moments. But all of these things can be presented in this kind of general setting. Okay? And the algorithm is as follows. Okay, you get some data that's corrupted. You take the empirical mean, take the empirical covariance of your data set, and you do exactly what the intuitions that I told you before would say. So I take the top eigenvalue eigenvector of sigma hat. So lambda is the top eigenvalue, so it's a spectral norm. So if lambda is not too large, then this fundamental lemma says that I can just output the empirical mean. So I just output empirical mean. And otherwise, I know that the bad points must be causing the top eigenvalue to be large. Like they must be the really ones that must be dominating this direction, which means that if I look in the direction of v and I just project everything onto this direction, and if I'm sufficiently careful, I can somehow remove or downweight the largest data points in this direction. Okay, and in general, to instantiate this for like an actual class, I need to tell you what it means to be not too large, and I need to tell you how to remove these data points. But this actually is more or less everything that we ever do. Okay, and again, the sort of picture that we have is like, if I project onto v in the case where the top eigenvalue is too large, instead of seeing like a nice Gaussian like I'm supposed to, or whatever sort of distribution I'm expecting, I'm going to see like this sort of weirdness in the tail. And so if I sort of like carefully choose a point to like throw points out, it turns out you can guarantee you throw out more bad points than good points, or something like this. Okay, and just to show you, just to like try to give a more concrete example of this, just to say that this is really all that we need. Let me again turn back to this setting where I have bounded covariance. Oh, sorry, I forgot. One thing I should say is that this algorithm is actually very simple to run, just because I claim this entire thing requires like a couple passes over the data. Because I'm saying you should take the empirical covariance of S, and you need to take top eigenvalue eigenvector of this covariance, which might be hard if you don't want to do SVD of a large data set. But it turns out in all the settings that I'm aware of, you only need a very rough approximation to the top eigenvalue eigenvector. So you can do power method, and this runs in like a couple of iterations over the algorithm of the data set. So this entire, like a single iteration of this, runs in like very fast. And oftentimes in practice, we found that you only need like 3 or 4 iterations of this. So this is like a very small overhead for this sort of robustness for free. Okay, but let me try to instantiate this bound for the specific case of bounded second moment. So recall, I have a distribution D with mean mu and covariance sigma, which is bounded by the identity. I'm going to assume that S is a corrupted set of samples from this distribution, and my goal is to recover some mu hat, which is roughly root epsilon. Let me assume that it's big enough so that the first term due to concentration goes away, and this is really an important term. So how do I instantiate this algorithm to get this sort of guarantee? Turns out it's quite easy. So first of all, I need to tell you what it means to be not too large. In theory, you can just take 9, although I think in practice you might want to tune this, and we do. And now we need to do this step. So let me tell you what mathematically means to project. It's a projection. You take v inner product x after centering for every data point x. So this gives you a score, tau of x, for every data point. And you square it, because I don't really care about, I'm trying to get the second moment information, so I should square it. Okay, so this is a very simple operation, and I let tau max be the max of these scores, just for fun. And then what I'm going to do is, this is a slightly kind of subtle thing that we need to do here. To remove, what I'm going to do is I'm going to remove each point in my data set independently with probability this, tau of x over tau max. Okay? Or if you don't like randomness, you can also, instead of doing a hard removal operation, just downweight each point. Just say, I don't believe you anymore. Just assign it a weight and downweight this point with some probability similar to this. Okay? And that's it. So you output the set points, and then you just iterate this some number of times, and it works. So this is really a very simple algorithmic, statement. The proof that this works is obnoxious, but from a purely algorithmic perspective, this is very simple to run. Okay? So that's very nice. And we can also instantiate this for other settings. So again, I've been focusing on the setting where the covariance is bounded, just because that's the simplest one. But you can do a lot of other things. So this is the one I've been talking about a lot. If you have bounded second moment, you can use the filter to get something which is like O of root epsilon. Another setting, which is considered a lot, is when the true data or the good data is Gaussian or sub-Gaussian, where you have much stronger concentration, and there you can get a much better bound. So instead of getting root epsilon, you get something which is like almost epsilon. Okay, another interesting setting, which is okay, it doesn't quite parse with the sentences I wrote there, but I couldn't figure out a way to make all of them parse in the same way. But I can do other statistics beyond mean estimation. So I can also do stuff like covariance, which is going to be very important for one of the experiments later on. So in particular, if I have a Gaussian and I want to learn the covariance of this Gaussian, it turns out I can learn this to error epsilon log 1 over epsilon. And this is not quite L2 error. This is actually something, because L2 error doesn't quite make sense for matrices. This is actually sort of like a Frobenius error. It's like a relative Frobenius error. It turns out to be the natural affine invariant notion of Frobenius error for this problem. But more or less, it's the right thing, and we get a very good answer again, epsilon, which is almost like information theoretically optimal again. Okay? And finally, another setting for this problem of estimating basic parameters is bounded second moments is sort of the weakest assumption. It's a very weak assumption. I shouldn't say it's the weakest assumption, but it's a very weak assumption that you can make on your good data. And sub-Gaussian is a very strong assumption you can make on your data. So the natural question is, can you interpolate between these two settings? And the answer is sort of. So if your distribution has bounded teeth moments, which is sort of a way of interpolating between this, because the Gaussian has bounded infinitely many moments and they're relatively small. But if you have bounded teeth moments up to some constant t, and your distribution is nice in some technical sense, related to the sum of squares hierarchy, never mind that, then you can sort of interpolate smoothly between root epsilon and epsilon. Okay. And I should say that for all these guarantees, these are the first efficient dimension-independent guarantees. So there weren't algorithms for any of these settings before that could achieve rates in polytime that didn't depend on the dimension in without polynomial factors. And I should also say that for all these settings, these rates are more or less optimal. No algorithm given any amount of compute or whatever can hope to beat this sort of guarantees. And there's many other settings that have been considered by myself and other people. You can read the list here or not, but there's a lot of different settings. Yeah. Okay. So these things work well in theory, but now we want to see how well they work. Yeah.
When I have this problem with outliers, say in 1D or 2D, I just use a median along each dimension. And so if I'm operating in low dimensions like that,
yeah. So
should I use median or should I use what you've got?
So yeah, as I mentioned this earlier, I guess, but in low dimensions in general, the problem of dealing with outliers is pretty simple, because you can use these relatively naive techniques, and you won't pay a dimension factor because there's no dimension factor. Sort of everything needs to be pretty close to the mean, otherwise it's going to look very suspicious. So really, this is a technique for dealing with outliers in very high dimensional data. Yeah. Which is really that was the much more algorithmically challenging regime.
So
Yeah.
what is the reason for you to downsample according to tau max? So tau max itself, it's not good enough of a score?
Well, I guess you want when you're downweighting, you don't want to make things negative, I guess, right? So you would want your beliefs. They're not really beliefs, but you can think of them as beliefs to stay between 0 and 1. And one way of doing that is to do this, for instance. Although there might be smarter things. I don't know. Okay. And this is actually related to some of the stuff that we've been doing. So, okay. So these things work well in practice or in theory. Question was now like, do they actually work well in practice? So we started investigating this. So we began with arguably the most basic setting, which is synthetic data. So what we do here was we took Gaussian data, I think in this case, and we took some fixed epsilon. I forget actually what the epsilon was. It's like 5% or 3%, something like this. And we added corruptions relatively naively to the data set. And then we ran our defense, which is filtering the black line, against a bunch of other known robust estimators. And we just plotted the error as a function of dimension. And this blue line is the concurrent algorithm by Lyra and Paula. Okay, so we plotted the error as you increase the dimensionality of your data. And as you can see, the other baselines really do suffer this root D kind of polynomial loss. As you increase the dimensionality, it gets worse. But ours and LRV do not. And when you kind of zoom in, ours does it performs very reliably better than LRV as well. Okay, but this is unknown mean, and I also mentioned we have algorithms for unknown covariance. So what we tried here was two different settings. So we tried a setting where the covariance is relatively isotropic, so it's spherical. We did the same thing. We generated Gaussian data with this, and then cropped it a little bit, relatively naively, and then did our algorithm, which is filtering against some baselines, and also LRV. Just plotted the error as a function of dimension. Yeah.
In the previous slide, you had ransack as a baseline.
Yeah.
You need a minimal model for ransack. What does?
So for ransack, we were just assuming the data is Gaussian. So then what you can do is just subsample, and then
the minimum you need to sample to ensure it's a Gaussian.
So you can take a subsample of any size, I guess, and you're going to get some estimate of the mean. Right? So in ransack in this setting, it's very simple. I take a subset of my data. I hope I've completely missed the bad points. I just take the empirical mean because that's the best estimator I can.
Can you compute the support for it?
You don't really need to even deal with that because all I'm looking for is an estimate of the mean, right? So if I have a data set and I've hoped that I've missed all the bad points, then my best estimator is going to be the empirical mean, more or less. Yeah. So ransack in this setting is just sample and hope I missed and take the empirical mean. Yeah. Somewhat unsurprisingly, it doesn't work very well. But yeah, so we have this setting as though we take the isotropic setting, and we also took a setting where the distribution was more skewed. Okay, and we ran all the defenses on all these settings, and we plotted the error. Mahalanobis error turns out is this relative Frobenius norm error, which turns out to be the right notion for this problem. And as you can see, so in the isotropic case, a lot of things do well, and ours kind of does the best as the dimensionality grows. But in the skewed case, we have a really marked difference. So when data is a bit skewed, I can't even plot the performance of these guys because they're up there. And ours is still almost 0, and they get very better. That's
Does the sample covariance work well with low dimensions?
The sample covariance works well just because of this reason that we constrain ourselves to have non-stupid kind of corruptions. As in, we want our corruptions to at least look a little bit plausible good points. So we constrain stuff like the L2 norm of our corruptions, just because otherwise there's very basic baselines just remove the largest points or whatever. And when you're in low dimensions, that causes it to not be too bad. Yeah.
Why do you think the skewed case is easier than isotropic?
So I'm not entirely sure what happened here. I think this is an effect of some sort of concentration that somehow some effects that we expect due to high dimensions didn't start to happen because of concentration. Also, in this case, somehow, I don't know. To be honest, for these are all synthetic data, so we didn't try too hard, in the sense that we just kind of these effects are pretty ubiquitous, and just sort of a proof of principle that sort of these things work. Yeah, I think the more interesting experiments for this stuff are the real data, which I'm about to come to in a second. Yeah.
Do you have intuition for what the error means? Do you have 0.4 or 0.2 or?
Yeah, so you can think of it as sort of total variation distance. Yeah, if you're familiar with that, a statistical error kind of guarantee. Yeah. Yeah.
I have a question going back to the algorithm. So you have this if condition. If the largest eigenvalue is not too big, then you're fine.
Yeah.
Is that if you didn't have that condition, if you just downweighted anyway, would you expect it to just minorly improve things and you just don't want to bother taking the time, or would it actually damage things if you didn't have? I'm just curious. What's the point of that if?
So what's the termination condition of the algorithm?
Yeah, it is a termination condition because I'm just going to run this over and over.
Oh, you keep iterating.
Yeah, I have to. Yeah, keep running this over and over. Actually, in practice, I think what we found was the most effective is not even have that as a termination condition, but just like literally have stop after 4 iterations as a termination condition, because it seemed to work for at least these things. This is not true in general, but yeah, in the end, if you like run this infinitely, forever and ever, this algorithm, as stated, will just like downweight everything to 0 eventually.
Yeah, I didn't realize you kept looping.
Yeah.
Right.
Yeah. So again, okay, yeah. Okay, so we did these nice synthetic experiments. They sort of validated the theory. That's nice. But like, does it actually work on real data? So we tried this setting called. We tried to do this experiment called genes mirror geography in Europe. So this is a very classic experiment by the November lab at Stanford, like 10 years ago. What they did was they took a bunch of genetic expression data, so the same type that I was talking about at the beginning of the talk, and they just took the top 2 principal components of this data, and they plotted it. And they took like European genetic data, and what they found was that, roughly speaking, after like rotation, like appropriately rotating the space, you get like a map of Europe back. Sort of, you squint a little bit. And this is like a little bit surprising at first. Like, why would this happen? But, at a high level, and this is actually apparently somewhat vetted, this makes some amount of sense in the sense that, you would expect that if you're like closer to people, you would kind of have more genetic similarity with them. So this is a nice picture, a nice visualization. But to get this picture, it turns out they have to be very careful with the data, which is like not surprising because this is a very nice picture. In particular, one thing they had to be very careful about, and they were clear about this in the paper, to be fair, was they had to remove immigrants from their data set. And this makes a lot of sense if you believe their hypothesis, because suppose I have a lot of immigrants from somewhere else in the world, they're just going to have some other kind of very different genetic data set, and they're going to completely destroy this more fine-grained structure that I'm looking for, right? So in this setting, you can think of immigrants or other sorts of like mistakes due to whatever as sort of outliers for your data set. And what they had to do to get this nice picture is like very meticulously go through every data point and just trying to remove the ones that like look like they might be of this sort. Okay, so what if you didn't want to do this? What if you didn't have access to this? Well, unfortunately, we didn't have access to like the full outlier data set with like all the immigrants, because that's like behind a bunch of NIH paywalls, or not paywalls, but like security walls. So we tried to like simulate the effect of outliers on this picture. So we actually very naively just generated points that kind of look like the points that we found. And when we do the same experiment, so project on the top 2 principal components of the data, you get junk. You don't get this nice picture at all, which is, not so surprising. This is very brittle, these sorts of other sorts of outliers. So how can we fix this? Suppose we didn't.
What sort of noise did you introduce?
It's like the same like picture more or less happened for like whatever noise that we got. It was like just product noise, product distribution with like attributes that looked roughly similar to the attributes that we found here. So like the mean looks pretty similar-ish, the covariance looks pretty similar-ish, but like not too similar, this kind of stuff. And then when you do this, you get this. But like the same qualitative behavior didn't really depend on the choice of like distribution that we get. So yeah, so if you don't like try to address this, then you get lots of issues. And it turns out, moreover, that like previous defenses, like previous techniques for like robust PCR or whatever, they all kind of get this picture. Okay, but we have this technique for robustly learning covariances. And the principal components of your data set, the top 2 principal components, are simply the top 2 eigenvectors of your covariance of your data set. So if I can learn the covariance in the presence of errors, I can simply read off the top 2 principal components robustly and project onto those. Right? And we have this algorithm for learning.
What was your error metric again for the covariance result?
So in theory, it was like this relative Mahalanobis distance. It's like you can think of it as Frobenius norm when things are well conditioned. But in practice, it's just yeah, whatever. So we tried that, and when you take these robustly recovered principal components. Even in the presence of noise, it's very nice that you recover something which looks more or less like a map of Europe. That's pretty nice. And this is like with pretty much no like pre-processing or anything like that. Okay. So that's pretty cool. And there's lots of work still kind of in this realm of kind of robust estimation. Oh, yeah?
I'm just curious, what would have happened if you ran your algorithm on the data set without any noise added? Would it like start removing the smallest countries out or something?
Yeah, it did that. It was actually really funny. When we did this, it removed Turkey because Turkey had 4 data points. And I think it still removes Turkey here. So, yeah. So it validates what we kind of expect would be happening as well. It's kind of nice.
Yeah.
Nothing against Turkey, though. No. Okay. Further directions in this this very specific field of robust estimation, there's still a lot to work on here. The first question is are these error rates actually typed for efficient algorithms? So I mentioned this table. I said that they were all, information theoretically, you can't improve. But I had this weird condition of niceness or whatever. Turns out that condition might be necessary. There's some complexity theoretic implications that's saying that you might not be able to improve this. But this is sort of, who really knows? Another question is that, this filter algorithm I had, it's nice. It runs in polytime and is pretty efficient per iteration. But in the worst case, you might need a lot of iterations because you're only looking one direction at a time. In the worst case, you might need to do this for each direction of your data set. That might require something like O of D passes, where D is your dimensionality. The question is, can you avoid this? It turns out you can. So this is actually pretty nice. You can kind of look in all directions in parallel. And there's some nice connections to matrix multiplicative weights and these quantum entropic regularization kind of stuff. And that sounds fancy. And the math for analyzing is correspondingly more annoying. But very nicely, the algorithms that we get are actually eminently reasonable. And actually, we're in the process of with Ihe, trying to see if they actually work well in practice. And so far, it seems they work pretty well. Okay, and a final thing, which is even less well defined for this setting, is unlike some other robust estimation techniques, this has the very nice property, our filter has a very nice property that we're removing outliers in a very strong sense, in an algorithmic sense. Not only are we doing robust estimation, but our algorithm literally just throws away points that look suspicious, right? And this gives us a very principled new approach to do outlier detection. The question is can we use this, in other settings? Can we make this statement rigorous, or can we actually use this for more generality detection in other settings? Some of the stuff I've already been saying says that we can. For instance, this experiment with Europe says, you can remove outliers in some sense. When you run our algorithm, we are more or less removing all the outliers that we're adding, and we're removing Turkey. But there's still a lot to explore in this space. There's lots of domains of application that I would really like to see if this works, and there's a lot to explore here. Okay, but there's also a big world beyond just mean estimation and covariance estimation. So there's a natural question can you go beyond this? Can we robustify much more complicated objectives supervised learning, regression or SVMs or whatever? And it turns out that you can. So let me phrase the problem in a general framework of the stochastic optimization. So hopefully most of you are familiar with this. But what you have is you have a loss function which takes a data point and your model W, and you have a distribution over your data set, right? And your goal is to minimize the expected loss of your model over this distribution. There's this function f of W, or also known as the risk, I think, which is, for a fixed model W, is the expected loss of your data from this distribution. And you want to minimize it. You want to find a minimizer of this function when you get samples from your distribution D. So this really encapsulates all these regression, SVM kinds of things. Okay, if I want this to be robust in the presence of noise, the challenge is given an epsilon corrupted set of samples from your distribution, no longer just IID, but corrupted. Your goal is to still minimize your function f. Okay, so can we do this? And turns out you can. And it actually builds on the techniques that we just developed. The first try that already works kind of okay in theory is the following. It just runs stochastic gradient descent using robust estimators. So what do I mean by this? So recall the following is SGD, which works quite well in a lot of settings, which is it's an iterative method. I have a current model, WT, and I update it. WT plus 1 is equal to WT minus the step size times the gradient of a fresh sample, XT, at my current model, WT, right? And this works. You can prove that it works. And in a sense, it works because you're taking steps which are an expectation of the true gradient that I would really like to move in the direction of, right? When there's no corruption. So this is all in the presence of no noise for now. But obviously, when there's corruptions in the data, this is no longer true, and everything breaks down terribly. Okay? But it turns out that we can use our techniques to actually fix this. Why is this? Because it turns out that if you look at the gradients, these gradients are a distribution whose mean is a property that we really care about, this gradient of f that we want. And these gradients are sort of corrupted, and epsilon fraction of them are bad. But we just want to recover the mean of this distribution, and I've just spent like a lot of time telling you how to recover means of distributions in the presence of noise, so it turns out you can just do that. So instead of taking a step in the gradient, in a stochastic gradient, take a robust estimate from your data set of the gradient and just do that. And this already works in theory, but it's a bit slow in practice, just because instead of doing a single stochastic gradient step at every iteration, I have to do like a full this filter process, and it's like kind of slow in practice. Yeah.
Two questions about that. So one is I'm trying to understand how the connection works in theory. So you the bound you stated for mean estimation.
Yeah.
It gives me an L2 error bound on the mean estimate.
Yeah.
But that estimate can up to that level be precisely say each time be pessimistic or optimistic estimate, right? And that will actually inject a fair bit of.
So I'll show you the concrete guarantees that we get in a second.
Okay.
But yes, I mean you'll have noisy gradients. Like this G sub t won't be an unbiased estimator, but it'll be a pretty.
And the bias is, the bias is going to be both dependent on, in a strong way, on the size of the mini batch as well as the epsilon, right?
So in theory, what you would do here is you need to take a really large mini batch for this algorithm.
I see. Fair.
So that's like one of the reasons why this algorithm is not great
I see.
in theory. Oh, sorry, in practice. And so we want to rectify this, the fact that you need to take very large mini batches to get this to work. And the idea, which I don't want to spend too much time on, is to do the following. Just take your data set and take your favorite training algorithm in the world. Okay, and just run your training algorithm to optimality on this corrupted data set. And then only at this point do you filter. Do you use anything to like remove bad points? And at a high level, this should work because the filter has two. It has one or two behaviors. Either it tells you that the empirical mean has to be close to the true mean of your data, or it throws out more bad points than good points. Right? This is sort of the high-level guarantee of what's happening. So in the latter case, yeah.
Don't you need to assume something then about the bias of the gradients? If you get to a minimizer of the empirical risk anyway with bias gradients, then you need some assumptions of the bias. Right?
Okay, so I guess like with this algorithm that I'm like sketching is what you're going to do is you're going to run some algorithm to get an empirical risk minimizer, do some robust mean estimation to like throw out outliers, and just repeat on the trim data until you converge.
But my point was that if you have any kind of bias in the gradients, you don't necessarily get an empirical minimizer.
Yes, you're not going to get
of the
on the training set. You're going to get the empirical risk minimizer on the training set. So you're going to get a point with gradient 0. Let's see. Okay. So in this setting, so if you throw out more bad points than good points, you're happy. Otherwise, your algorithm, the filter, certifies that the empirical mean of the gradients is close to the true mean of the gradients. Okay? But the empirical mean of the gradients is 0 because I'm at a local minima. And the true mean of the gradients is the gradient of f at my point. So it certifies that the gradient of f at my point is not too large. So at a high level, that's why it works in theory. And this is sort of the guarantee. And you can see there's some, this is sort of the term that you were referring to before. You're going to pay some term in terms of epsilon. But this is like both not too bad oftentimes and also unavoidable, at least in theory. And in practice, this works great, I should say.
Are you still expecting in this particular case that there's an underlying distribution of your uncorrupted data that has a certain mean and...
Yeah, I'm assuming, this is what I'm assuming formally. I'm assuming some mild regularity conditions on the true data. If the covariance is bounded, which is like a typical assumption in like...
In the case of I don't know, machine learning algorithms, is there a realistic assumption that there's this normal distribution data on the training data that
So this is the assumption I'm making. I guess it's like much milder than normality, just that the covariance of my gradients is bounded. Oftentimes, actually, in a lot of papers, you actually assume like a bound on the L2 norm of the covariance and this kind of stuff. It's pretty interchangeable. But these conditions, at least in theory, are actually pretty mild. And as we will see, they do seem to work. The algorithm does seem to work in practice.
So this is for the second version you showed, where you iteratively do the filtering.
Yeah. Although both algorithms sort of have this guarantee, just that the latter works much faster in practice.
And in this particular case, the source of corruption could be
anything.
Bad labels?
No, they can be anything. You can like you can like introduce new x's and labels or whatever. So you can do, but you can only touch an epsilon fraction of them. That's the only constraint. Yeah, so in theory, the bounds are polynomial, but not super tight, although you can get some tighter bounds in some settings. But in practice, this works really well. So we did a bunch of things. So we did two settings. We did ridge regression and SVMs. And what we did for both was we did both synthetic and real-world data. So in regression, we did some drug discovery data set, which is apparently standard. And what we did was, so it's a slightly different setup than what we did for like the robust mean and kind of stuff. We just took our data sets and did some poisoning attacks on them. And just plotted the performance of our algorithm, which is the black line, against and other sort of baselines as a function of epsilon. As you can see, for the data poisoning attacks on synthetic data, our algorithm is very nice. And similarly for attacks on drug discovery on real world data. And even if you sort of try to target the attacks against us in like the strongest way that we could figure out how to do, at least, our algorithm for ridge regression is also quite nice. Okay. We also did this for SVMs. So I think these results are quite compelling, actually, because it turns out for SVMs, there's been like a lot of work on trying to develop these data poisoning attacks to like decrease test accuracy. So like Jacob Steinhardt, Peng-Wei Lo, and like Percy Leung at Stanford developed like this huge suite of attacks against like a bunch of algorithms or in general to try to beat these defenses. And so what we did was we took this huge suite of attacks and we took a large set of baselines. We're only showing a couple here, but we did like a large set of baselines. And for each baseline, including our own, we found the attack that performed, like got the highest test error. And then we just plotted the performance of that defense and all the other defenses against this attack for every defense. So if you take a attack that was just like the worst against some other baseline, then their accuracy like shoots off to infinity, and ours is like nice. And even if you take the strongest attack against us, we're still much better than the other defenses. Okay, and this is on synthetic data, and we also did this on real-world data. So this is like Enron, just like very standard SVM data set. And again, if you take the strongest attack against some other defense, their accuracy goes really badly. But even if you target against us, we're like extremely competitive with everything else. And sort of we have to be, because we have theoretical guarantees, and these other ones don't really. Okay, so that's quite promising. And one final thing I wanted to talk about, which is even going beyond this even more, and really going back to the second example I had at the beginning of my talk, which are these backdoor attacks against deep neural networks, which is, by the way, incidentally, joint work with Brandon over here. So just to recall, the idea was, against these watermarking attacks, was the adversary injects a small amount of data at train time, and the goal is to inject a backdoor into the neural network such that like when you do a regular test image, everything looks normal. But I can like change a test image by a little bit, and by like a predetermined change, and then I can like get it to be misclassified as whatever I want. And these are like real. You can do these against C410 pretty easily. So I think here, we made an attack that makes airplanes look like birds if you have, I think, this little cloud-like thingy. And again, airplanes, cats, I forget actually well, there's some like very subtle watermark here. I think it's like over here, you can't really tell, but it is there. And if you do the right kind of train time corruptions at test time, it'll pick up on the presence of like one of these things and really misclassify very reliably. Okay, and intuitively the reason why these work, this is getting a little bit heuristic at this point, because the idea is that neural networks have extremely high capacity for getting train accuracy. In particular, if I inject like mislabeled data with like some signal for like why it's mislabeled, it's going to pick up on this and really just build this into the network in a very strong sense. So what the network is going to see is that the implanted watermark or backdoor is a very strong signal for classification. Okay, so it's going to really amplify the signal and make it very important. So that way, when it sees a fresh image, also with this watermark, it's going to like ignore everything else about the image and say, "Oh, watermark," and like misclassify the image. Yeah.
Just clarification. So when you say that you inject that, do you do it only for one instance of the class, or for like everything marked automobile? You get to put a watermark or whatever subtle thing.
Right. So what the attack model is, you have like the set of like airplanes and birds or whatever, and these are your training images. And I'm going to add a small fraction of additional training images, and label them as like airplanes. These are airplanes. I'm going to label them as birds, and I'm going to like maybe inject these or whatever you want to do. But it's like the same sort of framework where you like there's a small set of corrupted data.
But the original also gets to remain? Like
yeah, the original is going to stay the same. Yeah. Okay. But hopefully it makes sense like why these attacks might work in at least heuristically. Like the fact that these networks have so much capability for getting like good train accuracy suggests that they can memorize these sort of strong signals, and that means that adversaries can build these signals into your watermark or into your neural network kind of easily. And when you have these strong signals, then you get these backdoors. That makes sense? All right, so that's what I said. So as a result, when you kind of learn these, you amplify the signal and you get this very reliable backdoor. And these are like pretty insidious attacks actually, because like if I give you like if I give you a neural network that's been backdoored, it's not even obvious that I can like check whether or not it's been backdoored or not. It's like pretty hard because on a regular test image it looks completely fine. So how do we defend against these? Well, the idea is actually kind of simple. What we're going to do is we're going to take our corrupted training set and we're going to just feed it through until the representation level of the neural network. So we're going to train the neural network on this corrupted data. So it's going to have the watermark, and then just going to feed the training set through to the representation space. Now let me take the example of like poisoning cats with dogs. Okay, so there's going to be some. So like what we're going to do is we're going to have some. We want to inject a backdoor such that like if a dog image has like a specific kind of watermark, it's supposed to classify as a cat. So when we feed the training example in, what's going to happen is that there's going to be a bunch of cats which are really cats. These are just real cat representations from a real neural network that's supposed to say cats. Okay, but at the same time, because the neural network is somehow being like tampered with to like inject the signal of this watermark, there's going to be some dogs or some whatever that's going to have a watermark. And in representation space, the reason why they're called cats is going to be very different. It's going to be because of this watermark. It's going to, you're ignoring all the features of real cats and just like amplifying the signal of this watermark. And so in this space, it turns out that there's quite a reasonable separation between these. In particular, the distance between these distributions is sufficiently large that the empirical covariance of this distribution in representation space is going to have a very large eigenvalue, much larger than there should be. And that's really, at the base of it, all our algorithms ever needed to like figure out that there's corruptions. So we can just actually run our robust mean estimation algorithms or whatever on the set of representations. And this is going to look like a small set of corruptions to the mean. And it turns out that this works quite well.
But this assumes that your initial data set is balanced, right?
Yes, I think so. Although I think at least for most image tasks, they tend to be. I guess in general, what it really matters is that like it's an epsilon fraction of every individual like class overall.
Right, I see. Yeah, because like the top covariance directions capture could be capture multiple classes.
Oh, sorry. This is just I'm just looking at a single class of representations here.
Oh, I see.
Yeah. So there's no issue there.
Yes. Right. Yeah.
Okay. And you can see, in a bunch of experiments that this actually works. So suppose, so this is like I'm trying to target automobiles with dogs, and I'm allowed either 5% or 10% of poison examples at train time. And you can see sort of if I do nothing, then the natural accuracy is great because these are on test data. So natural accuracy is great. That's because the algorithms, the attack's not supposed to mess with natural accuracy. It's supposed to get roughly the right natural accuracy. But when I implant the watermark, 89% of the time, it's going to misclassify the data. So at the beginning, if with no defense, this attack is very effective. But if I just like run a single iteration of like the filter or whatever, I'm going to like remove almost all of the poison points. My natural accuracy is going to slightly improve. Well, it's going to be similar, and you're going to have like the watermarks completely removed. That's quite nice, and this happens for a lot of.
Would it be fair to say that this method is good to defend yourself about a particular poison that you predict will be there? So you can only defend against birds, but what about turtles? Now, can you defend against any kind of poison, or just that poison you are?
So as long as the attack is not sufficiently sophisticated enough to like avoid this sort of large separation in representation space, the points that are poisoned will look like outliers in this representation space in a way such that our algorithm could detect it. We're not claiming, we don't have like formal guarantees that like no attack can avoid this, but for now it seems like the attacks that we know of can't avoid this. Yeah.
Yeah, and how do you make sure the representation space actually separates out the features that you actually want to be separated? Like it could pick up some feature that's like just sufficiently distinct pattern.
Yeah, I mean, it's a good question. At least empirically, it seems like we don't know of attacks that don't have this property, I guess. It is interesting whether or not you can circumvent this, because unlike the other things in this talk, this doesn't have actual provable guarantees. It's more a heuristic, but it is nice that like there is some connection here. But yeah, we don't know for sure, I guess is the answer. It seems like it, for now, is a barrier, at the very least, to like designing new attacks of this sort. Yeah. And I should point out that like previously, nothing was known for defending against these sorts of attacks. Okay, that's more or less all I had. In general, what I'm working on now, and what I've been working on in the past, is just to develop a principled theory of this robust machine learning. Typically, I mean, against outliers and training sets, but I'm also interested in other settings as well. So one question I've been studying a lot is like these computational limits, related to these more mathematical questions. I guess everybody wants to know what's going on with deep networks, but there's a lot of interesting questions, in particular for like outlier detection and data poisoning for deep networks that we're investigating. And there's also like lots of interesting other connections with other models of robustness. Like when you say the word robust, like you can mean like a billion different things, and they're all like robust in some sense. Right? And there are very interesting connections with other notions of robustness that we've been looking at as well. Okay, that's more or less all I had. Thank you.
Any questions? I think we asked questions through the talk, so let's just thank the speaker again.